What do you do if a highwayman tells you, "Give me all your gold"? You push the button and call the insurance. What if they ask for copper also? You push the button and call the insurance again. What if you need some plastic sheets? Or a pipe? Or some cables? Dude. Well, here's how this works. If you look at the autolathe or any other printer and scroll down far enough, then you find this information. As you can see, these printers themselves can now be programmed. Okay, this is a few weeks old already. We can say we have a stack pointer. We can say execute a recipe, which is what I'm doing here. We can also say wait until next is valid when it comes to the resources the printer is available, or jump if next is invalid, or jump to an address in its stack where the commands are placed. Lock the device, eject reagent, we have also seen that already. Eject all reagents, that's also possible, like when you flip open the lever. Or what is this? This is information that you can find in the memory at these addresses regarding which recipes, which reagents are currently missing for a recipe. For ejecting all the gold and steel or whatever, what we first do, of course, is we define the manufactories. We have them available as numbers for our programming. Here I'm reserving two registers with a name. One that has the reagent, which is what will be ejected, and one that has the ingot, which is what will be displayed on the displays. Then I'm preparing the logic dial. I'm saying I want three values, in this case at least, this is the example that I chose, and then I want to read which value is currently selected. Then, based on the selection made, I want to prepare the reagent at ingot. So, if register R0, which is the selection of 0, 1 or 2, is not equal to 0, then I want to branch relatively by 3 lines, 1, 2, 3. If it's not equal to 1, then I want to skip these also, and so forth. So if all of them would be skipped, which can't happen in this situation, but I want to prepare, I will just initialize them with a 0. Otherwise, I will write into them gold, which is to be ejected, and the ingot is to be displayed. Because, stupidly, the reagent itself doesn't cause any display if you give that to the hash display. Then I'm writing the ingot value to the logic memory chip. The reagent comes later. This is the memory chip. And via the disk, I assigned it here to this hash display. The hash display is a circuit board that you can place in a console. A hash display shows an image of a hash, once you have selected the source of the hash. And the hash is just a number that refers to the various things that are in the game. And here, with the logic memory, you can just store a value, and this will then be the hash. I'm writing this value via the source code. The kit logic memory, by the way, has a second build, which is the hash generator. In this very situation, it's kind of the same thing as the memory, because it can be used to choose which hash it shall hold. It will just be a value holder, and here you can see all the things the game has to offer, all of them. La 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 la, endless. So this dial selects which value shall be written to this memory chip, and the hash display shows it then. You can also use the hash display to conveniently show what your arc furnace is currently smelting. So let's continue. Here I'm reading the button. Has it been activated? Equal to 0? Though then go back to start. Otherwise, I obviously want the manufacturers to eject whatever I've selected. And so I will say turn on and eject. As we already know, subroutines are very useful. You can prepare a value, run the subroutine will then return to this very point, execute the next line, and so forth. So we can say subroutine, do this thing. The subroutine starts, does it, then we say subroutine, do that thing. Then I sleep for 3 seconds to give the thing time to eject everything. There are probably more elegant ways to do this, like actually finding out whether the device is done. I don't know that yet. And then I turn them off and jump back to start. So that's the main loop. The main loop is we select whatever the hash display shall show. we see if the button is being pushed. If it's not pushed, we jump back to start. Otherwise, we eject, sleep, and turn the devices off again. Now let's see what turn on and eject does. Before I explain everything that's happening in here, let's do something that is always very good for learning. For example, when you want to know something in school, people are throwing it at you and you might not be ready for it. But on the internet, you Google it and then you know, because now you're open for that information. So before I explain to you what I'm doing here, let us create the will in your head to achieve this. So we want to eject a certain reagent. What does that mean? It means the program needs to tell the machine eject stuff and eject which stuff. That's exactly what we have here. Here we have the opcode. That's here. Eject reagent. It's the 7. Or here, for eject all reagents, that will be the 8, and so forth. So we have this value here. Then the thing knows I need to eject reagents. And also we have the information which reagent to eject. We can see that here in the source code. There's the reagent. We selected that up here with the dial, and I prepared reagent gold, reagent copper, reagent steel, and we also have the 7. But how does this work? We're not talking about multiple registers into which I write something and then the machine sees those multiple registers and then executes it. Instead, it is just one number. One number that has 64 bits, like computers these days generally have, 64 bits. And we can see here the numbers referring to the individual bits. This is the least significant bit, which if the entire number would be 0, if you flip that bit, then the entire number would be 1. And the most significant bit, if everything is 0, then we have 0 obviously, and if this most significant bit is 1, then we have 16 billion or something? Oh no, that was back then when we only had 32 bits. With 64 that's even way more. Anyway, that's how this works. So we have to compose the value out of these bits. We are saying the opcode, the 7, will occupy bits 0 to 7, which is 8 bits. And wait, I'm on the wrong one. Yeah. And the reagent hash is written to from bit 8 to 39, which means it is 32 bits. You can see that here. Width is 8 bits and width is 32 bits. So why am I doing this the opposite way in the source code? In the source code you first saw the reagent hash and then you saw the opcode, the 7. Here, I'm just writing into this register the reagent value that I've chosen with the dial. But here I'm shifting the bits of this number to the left. You know, the least significant bit is always on the right. That's how we think of these values. So we're shifting this to the left by 8, and the result shall be written into the same register. So effectively I'm shifting the bits off the register to the left by 8. Meaning that now I have achieved this situation. The reagent hash is now here, from bit 8 to 39. You might think, okay, what about these bits then? They are unused. Yes, the reagent hash value that I have in my hands will only use 32 bits. I can rely on that, because that's how the programmers of Stationeers have arranged all of this. The reagent hash that I've gotten will not use more than 32 bits. So by just overwriting the entire register with a reagent hash, I have indeed occupied at the most 32 bits. Now I've shifted them to the left by 8, and so this is where the bits are occupied. Some commands here actually require more bits to be set. Then you can already estimate what this means. First I write the highest thing and then I shift. Then I write the next thing. Then I shift. And then I write the next thing. And then I'm not shifting because that's the last thing. So what I have to do here to eject reagent, I first write the hash. Then I shift 8 bits to the left, and then I have to add the reagent to this. But how do you mix them? Here I'm ORing the 7 into this register. What does this mean? Well, if a bit is 0 here, and if a bit is 0 here, then the outcome will be a 0 bit in that place. If one of them is 1 though, then the outcome will be 1. And if both of them are 1, then this will also be 1. There are other such operations. These are Boolean operations. That's something you should generally know if you're a programmer. There's OR, there's AND, there's XOR, there's NOT. They are even more than that. But you don't need to know this right now. What you need to know is we overwrite the entire register with a reagent. We shift to the left by 8 bits, and then we mix some bits into this value that we have already. And the bits that we mix in here come from the number 7. So now they will be at the bottom. And then what do? We need to write the value that we have created into the device's memory. But there's only the put command and the putd command. Others don't exist yet, I don't know. The put command is for the screws, if you have something on those, but I don't use them. I mean, they're too limiting. And put directly means that you have to address the device by its unique identity number in the world. How do we get that unique identity number? Simple. We just say, I'm loading into whatever register from, and what is this? Well, here I'm saying move to register R0 auto. And what is that? That's the auto lathe device. So that is for load batch and write batch. That's the device type. So I'm saying load batch into whatever register from whatever device is currently in here. Could be the auto lathe, could be the electronics printer, the reference ID, which is the one objective identity number of the thing that is built in the world. If I have 2 auto lathes built in the world, they will have 2 different reference numbers. And then of course I have to do this again because it's a batch reading command. So now I have this identity number, then I can say turn the thing on. I could also have used the write batch for that, but since I already have the absolute identity, why not just do this? Write directly to that device on 1. Here I'm clearing directly the stack, the memory, and here I'm writing directly into the memory at address 0 this value that I created. In this device. And that's it then. This ejects everything, for example, gold from the auto lathe, pipe bender, electronics printer, and to a Manufactory. Which looks pretty cool, but is ultimately not that useful, because once you are this far in the game that you can program these things, you will probably have enough resources that you don't have to constantly do this kind of resource tango with your machines. But anyway, it's a cool feature to have. Now let's make 10 heavy cables. The way this works is rather simple. Execute recipe, opcode 2. So first I write what it is that I want to produce. Then I shift to the left by 8 bits to make room for the next value. Then I write the quantity that I want. I OR that into the register, of course. Then I shift to the left by 8 bits to make room for the next value that I want to add there. And that's the opcode for the recipe itself. The source code for this is way more elaborate, but it's only longer. It's not really more complex. So let's see what the main loop does. Start, yield, and then I'm doing something repeatedly. This, ignore this please. This, ignore. This, ignore. This, ignore. What I'm doing is I'm preparing a subroutine call. Initialize recipe selector. So this means this is about the dial where I select what I want to produce. And the part that you're supposed to ignore is kind of the same thing, except this is about the amount. So I'm saying the recipe that, or rather the selector for the recipe I write into register R0. So in the subroutine I can use R0 to read from this dial instead of, for example, that dial. Then the hash display, the memory chip, I prepare that here for the same reason. I will read that out down there. This is only the reference to the device. And then I'm saying the dial shall have four different values: 0, 1, 2, and 3. And then I prepare in register 3, 4, 5, and 6 steel frames, steel sheets, and so forth. This is not the most elegant way to do this. I just wanted to implement it in a working way. Now let's look at the subroutine. Here I'm telling the dial that is in R0 that its mode shall be R2. R2 is the value 3. We just saw that up there. So I'm saying the dial shall have potential values from 0 to including 3. Then I'm loading the current dial value, and then I'm checking, is the value not equal to 0? Then skip to here. Else execute this line. And what I'm doing here is I'm writing into the hash display source chip that has been assigned in the hash display. I'm writing to it whatever register R3 holds, which might be steel sheets, or depending on Manufactory might be cables, or maybe a backpack. Same here, same here, same here. Yeah, it's a bit coarse. I could rather use the stack to implement this, but I haven't yet talked about the stack, and a part of the reason is that I haven't understood it completely yet. So before I do that, I want to delve more deeply into that. Anyway, this now prepares this value in the hash display, but not just in the display, we can also print it, because the things that we want to print and show here are identical. We want to print iron sheets, we can show iron sheets. That's the same thing. Before, I wanted to eject the reagent gold. I didn't want to eject the gold ingot. That's just the way this is handled in the background with abstractions. You know, in the background, the device cares about getting gold. It doesn't care where it gets that. Obviously, you can also only put a gold ingot in the device, so that's weird, but that's in principle how this works. What you think in the foreground is happening, I mean, what the game pretends to be doing, is kind of what's happening in the background also. So it's more easy really to imagine that what happens to Stationeers is a real thing, because apparently it is. Anyway, let's continue here. So here I'm saying the autolathe printing amount shall be prepared here, that's the dial, and then we want to interpret it. There's this subroutine. I'm saying that the amount shall be, the amount of potential settings shall be 4, 0, 1, 2, 3. Then reading the currently set value, and depending on the value, I will say that I want to print 1, print 10, print 50, or print 100. That's an arbitrary decision I made. And then we return to the calling position. So for the autolathe now, we have read out which recipe is to be printed, and we have written that to the hash display memory chip, which also shows it on the hash display. And we have determined which amount shall be printed. So what's happening here? Well, the trigger button for the autolathe will also be put in here, so it can be checked in the subroutine print maybe. And then again, the auto hash will be put in here, so we can read out what the hash display's memory chip has to say. So that's what we then also print. And here is the printer itself. Here's the print maybe function. It very simply just says load a batch named into register R0 from structure logic button. Which logic button? The one that was handed to us via this register, whether it's activated. If that is equal to 0, we jump back to wherever we have been calling from. Otherwise, that's a debugging value. Otherwise, we load the recipe that we have in the memory chip into this register. Then we shift 8 bits to the left. We write the amount. We shift 8 bits to the left, and then we write the printing command into this, carefully not to destroy the bits that are already there. Then we're just getting the reference ID of the printer, we turn it on, we clear its memory, and then we write the value that we have composed into the device. So that is for the autolathe, that is for the pipe bender, this is for the electronics printer, and this is for the tool manufactory. It's all the same thing, and also shows you the blessing of subroutine. Yeah. And that's all for today.